If you are hard stuck trying to understand how MultiversX works from a high level, well, do not worry, because in today's video, I'm going to take you hand in hand through the technical details and also break down one of the most important technical aspects on the protocol, and that of course is sharding. So if you've never heard of that term before, and do not take that the wrong way, don't worry, I take you through this and more with infographics, and again, in a very easy to follow format. Now, a disclaimer, I actually use the term Elrond a lot in this video. Now, since I originally made that video, they've rebranded to MultiversX, so you can use those two names interchangeably, okay? Now, with that said, please grab a coffee. If you have a spare 15 to 20 minutes, you are not going to want to miss this video, even if you're just brushing up on knowledge that you already kind of understand, okay? So with that said, guys, thank you so much for watching. Now, if you did want to support me, please like, subscribe, and if you're feeling really frisky today, go down below and have a look at my Patreon. You kind of might like what you see down there. But if not, come say good day on my free Discord. Of course, the link is down below as well. With that said, guys, let's go. At a high level, what is Elrond? Elrond is a layer 1 protocol inadvertently competing with the likes of Ethereum, Polkadot, Cardano, and Solana for that glorious spot at the top of the castle. Elrond is highly secure, efficient, scalable, and interoperable, being purposely built for the future internet economy. Now, with enterprise level adoption in mind, its design is robust and the ecosystem is thriving. Not to mention, just over 2 years after their mainnet has been released, Elrond has accumulated over 300 partners and hosts the second largest node count of any smart contract platform at exactly 3,200 nodes. Second to that, of course, to Ethereum. Now, Elrond is designed to be adaptive to an increase or decrease in traffic, manipulating and directing resources to be as efficient as possible. Now, a beautiful side effect of that is that it has zero downtime, like literally none. And we'll get to why later on. Also, Elrond has negligible fees that average around 1/3 of a cent and arguably the easiest user interface on the market. Now, it's widely known within the Elrond community that the protocol has beaten the scalability trilemma, which for those of you who don't know, is pretty much a triangle that bounds most protocols within it. Now, in doing so, the team and developers have had their eyes set on bettering the ecosystem rather than constantly trying to perfect the code base. Now, this results in some awesome dApps that are easy to use and completely functional. Basically, all their free time is put into the ecosystem. Now, the way Elrond has conquered the scalability trilemma speaks to one word and one word only, and that's sharding. And no, not sharting, sharding. You fucking retards! It combines multiple types of sharding that range in difficulty to implement, from hard to what the fuck, as well as a unique consensus algorithm that was modified from an existing functional alternative. We'll get into what those are in a second. Now, the sharding method Elrond uses is basically using a much more sophisticated version of Ethereum's Serenity upgrade, and somewhat similar to Harmony's approach, but more on sharding in just a second. All right, well, let's just stop right there for a second, because I can literally hear what some of you are saying as if you're speaking in my ear. Every protocol technically does claim they're highly scalable, fast, and secure. And for anyone that's new to the space, believe it or not, we hear this shit all the time. But mark my words when I say that Elrond lives up to their tagline, in most part due to the following two aspects. The first is Adaptive State Sharding, which is a combination of 3 common types of sharding. We've got network, transaction, and state. We'll get into what they mean and how they work in a minute. And the second is their consensus algorithm called Secure Proof of Stake, which is a spin-off from the typical proof of stake algorithm most of you are familiar with, yet with a lot of added benefits, specifically for the benefit of the protocol. Now, if we're gonna put everything into a nice little nutshell, Vitalik gave these 3 the scalability trilemma, and they basically said, F you. So let's start with us. But in order to do so, we're going to have to explain sharding.
But what the f is sharding?
Good question, Jimmy. The term sharding originated from centralized databases, which coined the idea to increase network efficiency and scalability. Over time, sharding has made its way into the wonderful world of decentralized databases, aka Web3, being recently popularized by Ethereum's Serenity upgrade. Now, at this point, sharding is basically a crypto colloquial term, and it's safe to say most people have a rough idea of what it means. The thing is, not many people understand the distinction between the various types of sharding, or that there even is any. It's kind of like 2, 2, and 2, or weather, weather, and weather. It's very well easy enough just saying those words, but there is a lot more behind the scenes than meets the eye. In the broader sense, when most people refer to sharding, whether they do know it or not, they're likely referencing a combination of both network and transaction sharding. Now, this is perhaps because these two types of sharding are the most prevalent in blockchain tech, and in saying that, they are both used in Elrond. Now, network sharding, to explain, is pretty much the process of a network being partitioned into much smaller versions of itself called shards. Now, each shard hosts its own set of nodes which work together to operate similar to how a regular blockchain would, running their own instance of a ledger, propagating data, and forming consensus. Basically, you could say each shard is an independent functioning chain in their own right. Now, transaction sharding, on the other hand, is simply the mechanism that directs transactions to these shards, and it's usually implemented alongside network sharding, quite obviously. Now, this is important because oftentimes protocols will designate a shard or multiple shards to complete specific tasks. Now, speaking benefits for combining both network and transaction sharding is that the transactions can be processed in parallel. Now, the best way I can kind of describe this is if you were to clone yourself multiple times to write out lines in detention, obviously you'd get through it multiple times as quick. Now, the big no-no with limiting the protocol to only network and transaction sharding is scalability, security, and storage. That's right, we're still affected by the trilemma. Now, without getting into the nitty-gritty details, the nodes in each shard are still required to hold their entire state of the full blockchain, no matter what shard they're on, causing storage issues down the line, albeit way down the line, but they'll eventually come up. And also, scalability is still an issue, believe it or not, because of the same common denominator, and that is state. Now, this is mainly to do with smart contracts and cross-shard communication, or should I say, lack thereof. But to put it nice and simply, smart contracts are completely reliant on finality and communication to one another. And when you have to maintain the same state across multiple shards and the entire network, finality tends to increase and TPS decreases, leading to more trivial smart contracts. Now, let me just say right now, this mainly affects smart contract transactions. Now, security is also a very big issue as threats to full shard takeovers increase linearly to the number of shards you have. Now, if I'm going to give you an example, having, say, 1,000 nodes divided across 10 different shards would mean each shard more or less has 100 nodes. Now, you don't have to be a math genius to understand that a Byzantine attack is now accessible to 30 nodes rather than a full network of 300. Once a full shard takeover begins, a lot of the network can go down. Now, if I'm going to be cynical for a minute here, the only major benefit to a strictly network and transaction sharding database is that the network is able to process payment transactions much faster than if it were a single shard. Now, of course, protocols that strictly implement those two forms of sharding will have algorithms and methods in place to obviously optimize vulnerable aspects. However, none quite do the job as impressively as implementing what's called state sharding.
Well, why don't all protocols just implement state sharding?
Well, that's because it's fucking hard to incorporate. As a matter of fact, I believe Elrond was one of the very first blockchains to successfully implement state sharding. Not long before that, it was well and truly only theoretical. So what does it do? Well, I'm pretty sure if you were a betting man, you'd probably guess it sharded the state, and you'd be correct. Wow! So each node in a state sharded protocol is only required to hold the state of the shard it's on, not across the entire network. Now, this opens more doors than you can imagine. It allows nodes to have cross-shard communication as each shard will be distinct from the next, thus removing verification conflicts and allowing for smart contract transactions to be scalable as equal to that of their payment transaction counterparts. Now, storage is also no longer an issue for the longevity of the protocol as nodes are only concerned with the state of the shard they are working in. And Byzantine attacks are extremely difficult to coordinate, even for a shard that has reasonably low number of nodes. That's because security is increased by orders of magnitudes as the algorithm dictates that nodes are to be shuffled at the end of an epoch, which is approximately every 24 hours. Now, the shuffling process is completed in a completely non-deterministic and uniform way, which is pretty much just fancy words of saying at complete random. Now, this shuffling process requires no more than 1/3 of the nodes in any given shard to be redistributed during this time, as there is very real chances that a shard could fail due to offline or unresponsive nodes, so they tend to keep it within reason. Now, nodes that are reshuffled are then distributed to waiting lists on another shard, requiring synchronization to that new shard for an entire epoch, so 24 hours, downloading the new state of that shard. Once that epoch has concluded and synchronization is complete, the nodes are allowed to join the active validator set of that new shard, and they do not have to retain the previous shard's state. Now, at this point, it's basically impossible to take over an entire shard, as the randomness of the swap is only calculated in the preceding Metachain block. In plain text, that pretty much just means that nefarious actors only have about a 6-second window to know which nodes are being replaced and 24 hours to then collude that information and that sort of act. Now, trust me when I say this is definitely sounding a lot more easy than what it actually is, and that's a definite fact. The reason why most protocols stay away from state sharding is because it's extremely, emphasis on extremely, difficult to implement, as it introduces many different variables, including synchronization overheads, meaning network liveliness can be affected. But once implemented correctly alongside network and transaction sharding, you can create an insanely scalable layer 1 blockchain with no bounds at all to the scalability trilemma. Now, the reason why it's called adaptive state sharding is because the algorithm allows the protocol to dictate where and when resources are required. This mainly refers to the shards which can be spun up or decommissioned based on the network strain. I guess really, whatever is required to maintain network efficiency is able to be done, and it's a completely dynamic ecosystem. You can almost think of it like a pair of lungs, expanding and contracting when need be. Now, on Elrond, spinning up a new shard will increase the total network TPS by a value of around 5,000, which is quite impressive. Currently, the network has 3 active shards, which means TPS is around 15,000, with enough nodes in their back pocket to easily spin up a 4th or 5th if the traffic suddenly demanded it. Now, to give you an idea of how fast Elrond's TPS can go, in just its testnet phase, it managed to reach a whopping 260,000 TPS, which is quite obviously crazy by anyone's measure. Now, this is contrary to many other sharded networks, which usually maintain a specific number of shards at all times and having a maximum TPS threshold. Now, this information should be relieving to anyone like myself who obviously observes a project's longevity. If Elrond has the ability to spin up shards when the network requires it, it's able to infinitely scale, even well beyond their testnet limitations. When institutional demand eventually comes knocking on our very, very big door, TPS obviously will need to be extremely fast, most likely probably in the millions or the billions. And it's safe to say Elrond won't have to scramble to figure out how they plan to accommodate the monsoon of traffic. And that covers Elrond's ass. You know what, I'm sorry, I'll stop calling it by its acronym. Now, with that being said, I've left out one of the most important pieces of this very complex puzzle, a unique shard called the Metachain. Now, the Metachain technically is a shard, but it doesn't have the same operations as the other 3, which is pretty much how I told you they worked a second ago. It's designed to handle all network and global data operations, including facilitating cross-shard communication, nodes joining or leaving the network, node reassignment to shards, and final consensus on the blocks. This of course means the Metachain requires its own set of nodes, equaling the quantity found in the others. So what I more or less mean by that is these 4 shards each more or less have the equal amount of nodes across the whole network. So 800, 800, 800, and 800. Now, the majority of the Metachain's operation is consumed by notarizing what are called Miniblocks that are used to send transactions intra and cross shard. Now, Miniblocks are simply a bundle of transactions that are grouped together based on a common destination. This usually means they're grouped depending on what shard that transaction is being sent to. Miniblocks are bundled together inside somewhat of a conventional blockchain block, replacing the area you'd normally find in the uniform list of transactions. You could think of a mini block kind of like a shipping container, helping the Metachain identify where those transactions are being sent. Now, Elrond uses this block structure to allow for extremely fast cross-chain communication and finality times. It really only makes sense to identify what shard is receiving what transactions. Now, seeing as mini blocks are one of the most quintessential properties of the Elrond protocol and more or less gives us a bit of an insight into the 3 levels of sharding, let's break it down. Now, I promise you, if you stick with me through this, you'll be able to flaunt that knowledge to all of your friends. If you want, you can even ask all of mine.
Got it!
All right, so let's say we had an account on shard 0 and initiated a transaction to send some EGLD to a friend over on shard 1. Now, one of the first things that would take place is having our transaction grouped into one of these mini blocks. In this case, let's just say it's mini block 0. And all other transactions that happened on my shard that were being sent to shard 1 were also grouped into mini block 0. At that exact same time, any transactions that are being sent intra-shard, so within shard 0, are grouped into mini block 1, while transactions being sent to a different shard, let's just say that's shard 2, are then grouped into mini block number 2. Now, within that larger block, you'll also find mini blocks that have already been sent and processed from another shard, which will require our current shard to process and validate. And let's call this mini block number 3. Now, it's important to know that mini blocks are always processed atomically, meaning transactions that are within a mini block are sent 100% of the time or simply not at all. Now, this also doesn't mean that the entire block, meaning that larger block, isn't processed if a single transaction isn't atomically sent. The only penalty is that an individual mini block is retired until the next round. Now, for those of you who don't know, an atomic transaction is one that executes on both ends simultaneously or doesn't at all, which is extremely important for sharded protocols. So let's take it back a quick notch and imagine we have the only transaction of that mini block, and that individual mini block was the only one included in that larger block. Now, our shard, which is shard 0, would first process our transaction and update our balance, ensuring consensus is agreed on the state of your account, just like a regular chain would. And when I say consensus, I mean strictly consensus in shard 0. Now, this occurs in what's called a consensus group, which is formed from the secure proof of stake algorithm, but more on that later on. Now, once this transaction is approved on our shard, the Metachain is then sent the block header and the mini block as well. It's then the Metachain's job to notarize the mini block by including it into its own block called a meta block. Now, once that has been notarized, the meta block creates information about our mini block, including our shard ID, the receiver's shard ID, so that's our friend's shard ID, and the mini block's hash. Now, if we head over to shard 1, which is the destination shard or our friend shard, the nodes only require mini block 0's hash from the meta block, which is the proof the execution is complete on our shard, that's shard 0. Now, at the same time, shard 1 will also request the actual mini block directly from shard 0, so it can be used to verify the information. This is why it's really important that smart contracts operate on different states, because this pretty much couldn't be done otherwise. You can kind of imagine this like an auditor at your job, double checking all the paperwork to ensure you're doing things above board. Now, during this so-called auditing process, and that's obviously self-proclaimed, it's not actually called that, the nodes in shard 1 will complete a signature verification check, see if there was a replay attack, and request any missing transactions. Only then, if everything is successful, will the balance of our friend's account be updated. And just when you thought this whole process was finished, there's one more step. The transaction still needs to be finalized. Now, after our friend's balance was updated and there's no issues to be found, the same consensus group and block producer in shard 1 will execute the same mini block 0 yet again and send this back to the Metachain for the second time within a block header to be notarized. Once the second notarization is complete and consensus is met on the Metachain, only then is the transaction considered finalized. Now, once finalized, shards can request information about the blocks, mini blocks, eligible validators, nodes in the waiting list, and so on and so forth. It's there forever. Now, this process occurs in every round of every epoch, which is approximately 6 seconds long. Now, to be exact, a round is essentially just block time. That is the synchronized time every block is created throughout the network. So every 6 seconds, forever, a block is created simultaneously across all shards and the metachain. Regardless of whether that transaction is intra-shard or cross-shard, every transaction is to be notarized by the metachain at least once, irrespective of where it's processed or its destination. Now, if I'm going to summarize a cross-shard transaction in a single sentence, they're always sent asynchronously and the mini blocks are executed atomically. This just means validation and processing are done first in the sender's shard and then in the receiver's shard, with the metachain acting kind of like a verifier. Again, it's a notary. Now, my supersonic ears are able to tell me what the hell you're thinking. This all seems insanely long, right? Like, when is finality actually reached? Well, the answer to that is not long at all. Since each round is currently 6 seconds in duration, it takes around 20 seconds for an intra-shard transaction and about 52 seconds for a cross-shard transaction. Now, this does obviously depend on a few variables, but that's more or less about the timeframes. Now, finality, for those of you who don't know, is pretty important, as the lower a blockchain's finality, the more unique dApps you can build. Now, to put how impressive Elrond's finality is into perspective, a cross-shard transaction on Elrond finalizes almost 3 times faster than Cardano, 12 seconds faster than Polkadot, and 7.5 times faster than Ethereum, mind you, with a higher node count than all, obviously, except than Ethereum. So, if you've made it this far in the video, then I seriously have to applaud you. I know it's been a rough journey, so if you have a big glass of literally anything next to you, take a big f***ing sip of that. It can be very complicated talking about this sort of thing, but hopefully it does help a lot of you in your own research and give you an idea of how different blockchains run, because honestly, it's very simple just grouping that word into every single protocol in crypto. Now, before we move into some of the fundamentals, I wanted to briefly touch on secure proof of stake. This is how pretty much nodes, which are technically called validators in such an algorithm, form the chain and agree on consensus. Now, it's a standard in proof of stake algorithms that a validator's probability to confirm a block is proportional to how many tokens they are staking. Now, in such algorithms, centralization through monopolization occurs due to the rich getting richer and the poor remaining poor. Doesn't that kind of feel like how things work in our current society?
You're goddamn right.
But this tends to lead to validators leaving the network due to economic disadvantages, ultimately prohibiting protocol longevity and promoting centralization. Not only that, but a nothing at stake attack can occur, which is if a network hard forks, the validator's stake will then be duplicated across 2 chains, and they're now able to receive benefits from both networks at no cost, or worse, attack either one with 0 risk. So at Elrond's very core, an adaptation of Algorand's pure proof of stake was used to address these issues and then modified to suit the adaptive protocol architecture. Now, to keep it nice and simple for anyone falling asleep, secure proof of stake works by randomly selecting a set of validators to form consensus called the consensus group. Now, out of this random group, yet another random selection round elects an individual to be that block producer for that specific round. Now, for those who don't know, a block producer is a validator that creates the next block for the chain. Now, Elrond has this down to under 100 milliseconds, excluding network latency, of course, as there is no communication actually required for this process. The importance of choosing a block producer so quickly makes it basically impossible for an adversary to elect not to create that block. Now, if you're wondering why there's no inter-node communication in that round, well, it's pretty much because this is all elected in the block prior and actually from the protocol itself, not from a bunch of nodes choosing who that needs to be. Now, the block producer aggregates the required data into a block, of course, and sends this to the chosen group of validators for consensus. Now, this exact process occurs in every shard, including the metachain, and I guess takes that consensus time down quite a substantial amount as well. Now, by randomizing a group of validators for consensus, and from there the block producer as well, Elrond has basically removed all possibilities of DDoS and long-range attacks. Additionally, Elrond uses a rating system in combination with the stake factor common in all those other POS architectures. Now, the rating system is quite cool, and it works by evaluating overall reliability, performance, and responsiveness of each validator. Now, when a node or validator joins a network, they start with an initial score of 50 points, which is increased or decreased depending on what they do or don't do. And this score is never reset, even when the nodes are shifted to a new shard. Now, penalties, of course, are 4 times harsher than any gain, and the severity of the punishment or gain will change depending on their role for that round. Now, the ratings are on screen now, where the maximum rating is 90 to 100, giving a 20% more chance of being chosen, and the lowest being 0 to 10, with a negative 100% chance. This completely removes the monopolization aspect of proof-of-stake protocols, as everyone is given a nice fair chance to earn the rewards based on these conditions. What this means is that block rewards are equally distributed among all responsible validators, ensuring the ecosystem is economically sustainable. Now, if a node wants to leave the network, it's not because he or she technically is unfairly treated. It's probably because they were a shitty participant or the ecosystem is no longer growing. Oh, and before I forget, the really amazing thing about Elrond is that it's super interoperable. Elrond's virtual machine is built from WebAssembly, the state machine used in most Web2 platforms and websites, allowing for most programming languages to be used without additional barriers, and developers from all walks of life can build without much hassle. Additionally, a super critical component of the Elrond virtual machine is the compatibility with EVM, which is Ethereum's virtual machine. Now, this unlocks the capability for Elrond smart contracts to seamlessly operate with Ethereum and all of Ethereum's dApps. And not to mention, smart contracts written in the Elrond virtual machine are interoperable between many other chains, including Bitcoin, BSC, Avalanche, Polygon, Tron, Phantom, and a hell of a lot more. This was a no-brainer move from Elrond because Ethereum by far has the largest number of smart contracts built and used across the entire crypto ecosystem. Whether you're someone who loves or hates Ethereum, it's going to be the #1 smart contract platform for at least another 5 years, most likely even 10, and Elrond definitely knows this. It's a different story, for example, if Ether wasn't merging to POS and sharding, but I think the Elrond team understands that you've got to be interoperable to be the best, unlike other layer 1 protocols. Now, personally, I think a lot of layer 1 protocols don't bother trying to be EVM compatible as they see themselves as the so-called best, ultimately leading to some piss poor excuse for a bridge once they realize they were wrong. Cough, cough, Solana. And for simply those who don't have the resources or capital to scramble to find a solution like the wormhole, or simply they don't even bother, they tend to bottleneck what's called the L1 flywheel, as devs aren't keen to build on a platform with limited integrations, thus staggering the growth and bringing down the entire protocol. Thank you all so much for watching this video. If you found it useful, give me a like, subscribe for more of these types of videos, and I hope to see you all on the next one. Take care, guys. Thanks again.